In this video, we're going to take a look at what we call interval estimation. Up to this point, we've talked about obtaining samples from a population. And when we obtain those samples, the statistics that we observe are what we call point estimates. That means that it is a single value estimate of the population parameter. Now, just to recap, in a population, the variables of interest are referred to as parameters. In a sample, the equivalent variables are referred to as statistics. So when we get a sample mean, that sample mean X bar is an estimate or a point estimate of the population mean mu. So we want to now consider not just a point estimate, but an interval estimate. So for example, rather than saying that from a random sample of 100 students, we found that in a given semester, the average amount spent on textbooks is $550. So that $550, which is a sample statistic for the 100 students, is a point estimate of the true population mean. But there's a pretty good chance that there will be sampling error. That means that that sample value, that statistic, is going to be different from the population parameter. We can improve the estimate by providing an interval. So instead of saying $550 is the estimate of the true population mean, we could say somewhere between $500 and $600. So we now have an interval. And we could ask ourselves the question, well, if you have this interval estimate, how confident are you that the true population parameter is in that interval? So this is where we get to the concept of confidence intervals. So all of that will be introduced as we go through this particular lecture. Before we go any further, I just want to refresh your memory on a couple of things that we're going to be using. So the first one, of course, is the idea that we have a population parameter. The population could be normal, but it doesn't have to be normal. And that if we took a sample from that population, we'll observe a sample statistic. In this case, if it is the mean we're talking about, then X bar is a sample statistic which estimates the population parameter mu. And we said this is just a single point estimate. If we have a population that has a true proportion pi, and we took a random sample, and we observe the sample proportion p bar, then p bar is a point estimate of pi. Okay? So point estimate. So these are just these single values. An interval estimate, however, would require that we take the point estimate and we add and subtract some value to it. And the question is, what is that value? What is that value? And the value that we will add to it will be such that it will help us to estimate the population parameter with an interval, but we have a certain amount of confidence in it. In other words, we might say we are 90% sure that the true parameter is contained in that interval, or we are at 95% sure or 99% sure that the true parameter is in that interval. So it brings us to the idea of what we call confidence intervals. Now, before we make the leap, I want to just refresh your memory on the empirical rule, the idea behind the empirical rule. So let me just take a look at that one more time. You may recall that when we talked about the empirical rule, we said basically if we have a population that we believe is normal with a mean, mu, and standard deviation sigma, then about 68% of the values fall within one standard deviation. So basically mu plus or minus sigma is about 68% of the values falling in that range. Mu plus or minus 2 sigma, well, about 95%, but 95% falling in that range. And then mu plus or minus 3 sigma, but 99.75% falling in that range, just about everything, all right? is in there. That's kind of a very useful concept, because we need to be able to apply it in the context of sampling distributions now. So this was for a population. Let us consider a sampling distribution of a sample mean, for example. So if we have a sampling distribution of a sample mean, the mean of the sampling distribution of the sample mean would be mu x bar, and this would be sigma x bar. So I think we could say similarly, we have 68% of all the possible sample means that could be generated from that population. Now note the difference. All the sample means, I'm talking about when we generate different means now, then 68% of all of the possible sample means will be in that range. And then we get 95% approximately would be within 2 standard deviations, right? And then 3 standard deviations, we have the 99.75. So how would I write this? I would write mu x bar plus or minus sigma x bar. 1 standard deviation, mu x bar plus or minus 2 sigma x bar. So that would be your 68, 95, and mu x bar plus or minus 3 sigma x bar. So why wouldn't the empirical rule apply here? It should, because the sampling distribution, if we assume that it is approximately normal, right? All we're doing is we're changing the variables. Instead of using mu and sigma, we're using mu x bar and sigma x bar. That's all there is to it. Now I'm just going to just modify this a little bit. So instead of saying mu x bar plus or minus sigma x bar, what if we express it in terms of the population mean and population standard deviation? You may recall from our many theorems, the first limit theorem, the central limit theorem, and so on. So the mean of all of the sample means would just be mu, and the standard deviation of all of the sample means would be sigma over root n. All right? If we're talking about 2 standard deviations now, plus or minus 2 sigma x bar, then that becomes mu plus or minus 2 sigma over the square root of n. And that would be your 68 approximately, 95 approximately. Notice the term approximate, because we're going to have to do a little correction. Because if we want exactly 95, it turns out for a normal distribution, this would have to be 1.96. And that's why we usually say 2 standard deviations is approximately 95%, but it's actually more than 95%. And then mu x bar plus or minus 3 standard deviations. Well, in terms of the population, we would represent it this way. So what do you notice about this applying the empirical rule in this fashion? What we have is the population parameter, and then we have a value here which adjusts just how much of the area we capture. So when it's 1, it's 68%. When it's 2, it's 95. When it's 3, it's 99.75. And then we have what is here is the standard error. So a factor times the standard error. So the intervals that we're producing are a factor times the standard error. Okay? Now I want you to just keep this concept front and center. 68%, 95% if the sampling distribution of the sample mean is approximately normal. But you know what happens is that whenever we take a random sample, we never truly get the, we get a sample statistic that is that has a sampling error to it. We're never going to predict, or I shouldn't say never, very rarely will we be able to predict mu exactly. We will come close to it. There is a sampling error. And so why don't we just pretend, that the sample mean that we get is like mu, and the sample standard deviation is like sigma. And if the sampling distribution of the sample mean is approximately normal, then we could generate those intervals as well. So what the point I'm trying to make here is that, remember, we did it for the empirical rule, we did it for a sample, but we use x bar plus s, plus or minus s, x bar plus or minus 2s, x bar plus or minus 3s. This time we're thinking sampling distributions, in which case we wouldn't just say x bar plus or minus s, we would say x bar plus or minus s over root n. In other words, we have to mimic what we did here for the sampling distributions. So let us see what I'm talking about. So instead of, you remember how for just for a single sample, when we applied the empirical rule the first time, we said plus or minus s, x bar plus or minus 2s, x bar plus or minus 3s, okay? And that's when we were trying to kind of basically mimic the population distribution itself. But this time we're more interested in the sampling distribution. So since we are interested in the sampling distribution, what happens is if we have a sample mean of x bar and a standard deviation of s and a sample size of n, then if the sampling distribution is approximately normal, but we don't know what mu and sigma are, we could sort of pretend then that we could take x bar, which is our estimated mu, plus or minus 1, and then instead of just sigma over, instead of s, we now have s divided by the square root of n. So you see, this formula would have approximately, one standard deviation, would have approximately 68% of all of the data, of the sample means. That's that's an estimate here. If we take twice the standard error, and remember the standard error is just another name for standard deviation, but of the sample means, then we have 95%. And then if we take 3 standard errors, then we have 99.75%. So you could see here that this is kind of equivalent to what we had before, which was mu plus or minus sigma over root n, mu plus or minus sigma twice sigma over root n, and then mu plus or minus 3 times sigma over root n. All we've done is just wherever we have sigma, we replace it by s. Wherever we have mu, we replace it by x bar. That's because we only have a sample, and we have to pretend the sample estimates are the population values. So in essence, if we were applying the empirical rule concept to sampling distributions, where we only had the sample mean and the sample standard deviation, this is what we would do, and say that 68% of the sample means would fall in that range, 95% would fall in that range, and 99.75 would fall in that range. Okay, so that, folks, is what we're going to come back to, because when we develop the formulas for a confidence interval, right? These are the formulas that we will be using pretty close. These are the formulas that we'll be using. Okay, so think about it. The same way we apply the empirical rule concept using the sample data to try to determine the percentage of the population values within that range, the ranges, we could do the same thing by using the sample data, but we are trying to find intervals for the percentage of means, sample means, that are in that range. So just to clarify this a bit, so for example, when I have a range like x bar minus 2s, for example, and x bar plus 2s, what I'm saying is that the values, 95% of all the values, but notice I'm using x. which are individual values from a population. But if I did it this way, x bar minus 2s over root n, and x bar plus 2s over root n, then the variable that is supposed to be in that interval is x bar, the sample means. So this interval will have 95% of sample means, but this interval here would have 95% approximately of population values, individual values, not means, but individual values. Okay? So now let us take this concept of the empirical rule, and we'll see how we will build from it and develop confidence intervals for the true population parameter. So we're going to start off by looking at what we call estimating the population mean. When the mean, okay. So let us reflect on some terms. Point estimate, a single statistic determined from a sample that is used to estimate the corresponding population parameter. Okay, so x bar and mu, or p bar and pi. The sampling error is the distance or the difference between the sample statistic and the population parameter. And typically that sampling error will not be zero. So there will be some difference between those two values. A confidence interval now allows us to create an interval estimate and assign a confidence level to it. So for example, if we just reflect on the same concept as the empirical rule, when we say that when we take the sample statistic and add plus or minus 2 standard deviations from that statistic, then we have a 95% of the possible values falling in that range, if we assume the sampling distribution is approximately normal. Well, when we say that 95%, another way of referring to that 95% is as a chance. The chance of being in that range is 95%. We could then also refer to that chance as a confidence level. So if somebody says, well, how confident are you that the true value is in that range, or that the means are the sample means are in that range, you will say, I'm 95% confident, which basically means that there's a 95% chance that the values are contained in that range. Okay, so that's kind of where we come up with this term confidence. So the confidence level, in essence, is really the number of standard deviations, is related to the number of standard deviations that you're going to add and subtract from the mean. The more standard deviations you add and subtract, then the wider the interval. The wider the interval, the more confident you are. The less standard deviations, so for example, when we just use 1, right? If we only add and subtract 1 standard deviation, that's why we are only 68% confident, or only 68% of the values will fall in that range. So in essence, our confidence level should only be 68%. When we go 2, we're increasing the width of the interval. We're now talking about 95% confidence. So the confidence level is a value that expresses, in a sense, the probability that the interval contains what we're looking for. All right. So confidence is another way of saying the chance, okay, or the proportion of values that are in that range. So as you could see here, we have our point estimate, and what we do is we add a given amount, and a given amount, for example, when that point estimate was x bar, if we wanted, say, a 95% chance of the values being in that range, or 95% of the values being in that range, then we took 2 standard deviations, either 2s if you're talking about a population, or 2s over root n. If we happen to know the population standard deviation, it would be 2 sigma over root n. All right? And then here we would subtract from x bar, so that would be x bar plus that, and we would subtract from x bar to s over root n, or sigma over root n. Right? or 2 sigma over root n. So in other words, twice the standard error is kind of what we're looking at. So that's how you create a confidence interval, is by adding and subtracting a certain number of standard deviations. And the number of standard deviations will tell you, or will help you determine, what the confidence level is, or the probability that the interval will contain the parameter that you're interested in, or the percentage. Percentage is the same as probability, is the same as the confidence level. All those terms are completely related. So typically we have in terms of parameters and statistics, the population parameter mean, mu, it would be x bar would be the sample, and then when it is pi for proportion, p bar will be our sample proportion. We have 2 cases under which we attempt to determine an interval estimate for the population parameter mu. One is when we know the population standard deviation, and 2, when it is unknown. We will start off by dealing first with the case where we actually know the population standard deviation. It's kind of interesting because it's difficult to know the population standard deviation without knowing the population mean, particularly when you need the mean to calculate the standard deviation. But anyway, we're going to just ignore that and then just say that we want to estimate the mean. We happen to know population standard deviation. And so that's case 1. So a simple random sample is drawn from a normal distribution. Case 2, the population does not have a normal distribution, or the distribution of the population is not known. In both cases, the sampling distribution of x bar is assumed to be normally distributed. So if we're talking about the case where we happen to know the population standard deviation, then we automatically assume that the sampling distribution of the sample mean is normally distributed. In fact, we're applying the first limit theorem to that. And that will influence now what our confidence interval formula actually look like. So let's explore this idea of the confidence level. It's sometimes it could get fuzzy for some people. So we do know that if we took a population where we know the mean and the standard deviation, we could actually calculate the probability of a particular sample mean being within a given range. We could calculate that by using all the formulas that we used from before. And then this percentage would just be the probability that the mean is contained within a specified interval. To see this, let me just show you what I mean. So if we have this population, mu, sigma, and the sampling distribution of the sample mean would be mu x bar, sigma x bar. Well, if we wanted the probability that a sample mean would be in that range, we could compute that. We could just call this value here would this would be some particular value. Let's just call it it would be mu, x bar plus z sigma x bar. And z is just the number of standard deviations it is away. It would be mu x bar minus z sigma x bar. So that z just represents how many standard deviations is the value away from the true mean. Okay? And based on what z is, if z is 2, then we would have about 95% of the sample means falling in that range. In fact, the true value, as I mentioned earlier, is really 1.96, and then this becomes 0.95. If we use 1.96 standard deviations, we really get 95%. 2 standard deviations is a little more, but we just use that in the empirical rule. So it's important to understand that we could always calculate the probability that a potential sample mean would fall within a given range. That we know for a fact. But what happens now is that if we did the following, and this is where the confidence level idea comes in. I'm going to do this on a slide here. Let's say this is our population with mean mu, standard deviation sigma. What happens is that as we take a sample, let's say our sample mean is here. So we could see there's a sampling error, of course, between mu and x bar. This sampling error here. If we add and subtract a fixed amount, say for example we did x bar, because we don't know what mu is, x bar plus or minus, say, let's just say for now 2 standard deviations, 2 sigma over root n, if we happen to know sigma, x bar minus 2 times sigma over root n. Okay, so what happens is, notice that the mean, I'm going to just keep going on here, this is where the mean is. What if we took we got another sample mean and it fell here and we generated the same interval? What if we got a sample mean over here? We generated the same interval. If we got a sample mean here and we got the same interval, meaning that we add in 2 standard errors or 2 standard deviations away from the mean. If we got one here, it would be like this. If we got one here, so you notice that some of these intervals happen to have the mean, some of them don't have the mean. So for example, this interval here does not have the mean in it, right? However, this one does. This one does. I could create another one that's out here, x bar. And as you can see, this would definitely be an outlier. So if, for example, we were using 2, we say approximately 95% of all the possible values are in there. So, of all the possible sample means are in there. So the idea is that when we take a random sample, if we took the sample statistic and add and subtract 2 standard deviations to it, there is, because 95% of all of these intervals contain the true mean, then there's a 95% chance that that interval contains the mean. So if I took any one of those, there's a 95% chance. Here's another way to think about it. What if I created 100 of these intervals based on 2 standard deviations? Now, 2 standard deviations is approximately 95%. We know it's not exact, but it's approximately 95%. So if I did 100 of these intervals, according to our rule, 95%, approximately 95% of these intervals, 95 out of the 100, should have the true population parameter, right? Good. So what if I just randomly picked one of these intervals? And that's actually what happens to us when we take a random sample and we compute a confidence interval with it. If I happen to pick one of these intervals, then because I know 95% of them, 95 of them have the true population parameter in it, then there's a 95% chance that the one that I selected has the true population parameter. Okay, so let me just go over that again. So the idea is that you have a population of a mean and standard deviation. You could take a random sample, and using the sample data, S and X bar, you could compute an interval. Depending on the number of standard deviations that you use, 1, 2, or 3, or whatever else, there would be a certain probability or a certain proportion of the means falling in that range, right? Now, what we're saying is that if we were to just generate, as an example, 100 of these intervals, and we generated them using 2 standard deviations, because we know 2 standard deviations is associated with approximately 95%, then 95% of that 100, which means about 95 of those intervals, should contain the population mean. Okay, 95 out of 100. So if I randomly selected one interval, and that one interval would be the one that I got from the sample. I took my sample, I took my x bar plus or minus 2 sigma over root n. Well, that's one interval only. What if I randomly got this interval? What's the chance it contains the true population parameter? Well, 95%, because we know that 95 out of that 100 contains the true parameter. So if I randomly selected one, then there's a 95% chance it contains the true population parameter. And that is the idea behind confidence intervals. So whenever we get a sample and we observe the sample statistic, we could use it and create a confidence interval with it. And that confidence interval has a chance of containing the true population parameter. So now we need to focus on how to go about calculating the limits based on a particular confidence level. So we need a couple terms. One is what we call the confidence level. Okay, which we define as 1 minus alpha. And we will define it as follows. It is the probability, the confidence interval contains the true parameter. So we use 1 minus alpha, we call it the significance level. Alpha. So 1 minus alpha is confidence, 1 alpha is significance. And so the significance level is the probability the interval does not contain the parameter. Okay? We call it the significance level, alpha. So to draw this for you, it would look something like this. So let's say this is our confidence interval. We would take x bar. This would be x bar plus or minus z sigma over root n. X bar, not plus or minus, sorry. That should just be plus. Plus over here, minus over here. To z, we're going to use z, and I'll explain why we use z shortly. So if we do this, this area right here is the probability that the interval contains the true parameter. That would be our 1 minus alpha, our confidence level. However, the area in red would now be alpha over 2. Alpha over 2. Why? Because what's left is alpha. If we remove the center part, which is 1 minus alpha, what's left is alpha, but alpha is divided between the two tails. And so therefore, this is alpha over 2 in each of those tails. Let's just do a numerical example. So if we were talking about a 95% confidence interval, if 1 minus alpha is 0.95, that's a 95% confidence interval, then what's left? 5%, but the 5% is distributed between the two tails. So alpha over 2 would be 2.5% each, which is 0.025, 0.025. Okay, so that is what we would get in terms of trying to describe this. 1 minus alpha is the confidence level. Alpha is the significance level. But in a confidence interval, we have to take the balance, which is alpha, and split it between the two tails. So each of them get alpha over 2. What's the use of that? What's the significance? Well, depending on what confidence level we want, we could figure out, notice that this area right here, and I'm going to just shade it in black, will tell us what the Z value is. And that Z value is called a critical value. And it tells us how many standard deviations is associated with our confidence level. So if we want 95% confidence, it's approximately 2, it's not exactly 2. So we would have to be 2 standard deviations away from the mean. If we wanted 98% confidence interval, I will show you how we will calculate this, and then we would need to be 2.33 standard deviations away from the mean. If we want 99% confidence interval, then we need to be 2.58. And you'll say, well, how did you get that? Well, here's what happens. If you were looking at, say, a 95% confidence interval, this is 0.95. What happens is that the half of 0.95, which is what our table uses, this area would be 0.475. When you look up this area in the table, you get 1.96. And that's why we've been saying approximately 2, but it's really not 2. Z is 1.96. So to get a 95% confidence interval, we'll need 1.96 standard deviations away from the center value, right? Let's do another one. If we now want a 98% confidence interval, well, if this whole area is 98.98, then half of it would be 0.49, the blue region. So the blue region is 0.49. If this is 0.49, when you look up the Z turns out to be 2.33. So we need to be 2.33 standard deviations away from the center point to get a 98% confidence interval. Sometimes we consider a 90% confidence interval. So this area is 90% of all of the values, 0.90. So if it is 90%, we are going to need this shaded region to find Z. And it turns out that Z is 1.645. And last one that is very common to us is when 99% confidence interval. So 99, we have just about everything in there. So this entire area is 0.99. But if we shade this region, which is what our table uses to give us a Z value, the number of standard deviations we would need to be away from the center value to get a 99% confidence interval, Z would have to be 2.58. So of course, the larger Z gets, the more confidence we have in what we're doing. All right? So those Z values actually can be referred to as what we call critical values, in the sense that the Z value determines how many standard deviations away from the point estimate we want to create that interval. So plus or minus 2 standard deviations, 3 standard deviations, and so on. And so we refer to that Z value as a critical value. And we see here, so for example, in the case when we want a 95% confidence interval, our critical value will be 1.96. So I've explained that already on the last slide. This is 0.475, which gives us a Z value of 1.96. And if we wanted different levels of confidence, then of course the Z value, the critical value, has to change. So if we want to look at a general format for a confidence interval, you notice that it's made up of 3 parts to it. The point estimate, That point estimate is like your X bar sample mean or sample proportion. The critical value, which is the Z value for us, and the reason why we're using Z is because the sampling distribution, we assume that that sampling distribution is a normal distribution. And then, of course, the standard deviation or the standard error, which is the third part. And that would be like your sigma over root n. So if you look at the formula for the case where we want to find a confidence interval for the mean mu, when the population standard deviation is known, here's our point estimate, here's our critical value, here's our standard deviation of the population, but this term here gives us the standard error of the estimate. That's like the standard deviation of the sample means. Okay? N is the sample size. So if we understand this, we can now go ahead and do some problems where we are attempting to estimate the population mean mu. So just something to keep in mind that if we were looking for critical values based on the confidence level that we want, these are some very common values that we use. So I suggest that you could memorize them. If we were looking at an 80% confidence level, then in that case our Z value would be 1.28. If we're looking at a 90% confidence level, 1.645, 1.96 for 95, 2.58, but we're missing one there for a 98% confidence interval would be 2.33. So we could sort of add this down here. 98% confidence interval, Z is equal to 2.33. Okay? And we could actually find those values in using Excel, a particular function that could help us calculate the Z value based on the area. It's called norms inverse function. Okay? So the following are the steps that we will take when we want to find a confidence interval estimate for a population mean when the population standard deviation is known. One is we define the population of interest and select a random sample of size n from that population. Secondly, we specify the confidence level, and that's your sort of 1 minus alpha here. Compute the sample mean, which means that we'll compute X bar. Determine the standard error of the sampling distribution. So either that will be S over the square root of n if that's our best estimate, or sigma over the square root of n if sigma is known. In this case, sigma is known, so we'll be using sigma over root n. Determine the critical value Z, and the reason why we're using Z is that we have a theorem that states if the population is normal, the sampling distribution is also normal. But regardless of the population, if the standard deviation sigma of that population is known, the sampling distribution is also normal. So we are applying the first limit theorem. So we determine the critical value Z, and then we compute the confidence interval estimate. So these are the steps that we will undertake to obtain an interval estimate or confidence interval estimate for the population mean mu. So consider the following example. We have a paper manufacturer has a production process that operates continuously throughout an entire production shift. The paper is expected to have a mean length of 11 inches and a standard deviation of the length of 0.02 inches. At periodic intervals, a sample is selected to determine whether the mean length is still equal to 11 inches or whether something has gone wrong with the production process and a change might be required. So let's understand what is expected. It is expected that the mean length of the paper, Length of the paper, is 11 inches. 11 inches. And that it would have a standard deviation of 0.02 inches. All right? We're told that a random sample of 100 sheets, so our sample size is 100, yielded a sample mean of 10.998 inches. We want to find a 95% confidence interval for the mean length of a sheet, mu. So when we look at this data, what do we know? Well, we expect the mean length to be 11 inches, but we're not sure. So in that case, we will assume that mu is unknown. However, we're told the standard deviation is 0.02 inches. We took a random sample of 100, and the sample mean is 10.998. Find a 95% confidence interval. Well, the confidence interval for the mean of the population when the standard deviation is known is given by point estimate plus or minus the critical value, which is z, times the standard error, which is sigma over root n. And the reason why we're using z is because the sampling distribution of x bar is normal. So we're going to use z. All right? So that's the confidence interval. The question is, if we're looking for a 95% confidence interval, what is the critical value? And I'm just going to show you again how we find that so that you know how to compute z. But because 95% is such a common value, we tend to memorize it. We know z is 1.96. But let's see why z is actually 1.96. Okay. So if I were to draw the normal distribution, and I said I'm looking for a 95% confidence interval, which means that the area in blue, that's my interval, my lower limit of my interval, my upper limit of my interval, and we're going to take the sample mean and create the interval with it. What happens now is that our textbook, remember, will only work with this area. So since the confidence level is 95%, we know that the total area is 0.9, in the shaded, the blue region is 0.95, right? This is the area covered here in blue. However, this area in red is half of that because it's symmetrical, so it's 0.475. If you go to look up the table, the Z table, and you look up, try to find 0.475, remember that's the area, in the body of the table, you will find 1.9 and 0.06. That's where you will find that number, 0.475, which means that our Z value is 1.96. So to get a 95% confidence interval, you must take the sample mean or the point estimate and add 1.96 standard deviations. Okay, or and when I say standard deviations of the sampling distribution of x bar, which is basically sigma over root n. So that's 1.96. So let's substitute our values then. Our sample mean was, so confidence interval for mu, we already have the formula right here, so it would just be, our point estimate is 10.998 plus or minus what is our Z value, 1.96, or our critical value, and sigma is 0.02 divided by the square root of 100. That actually gives us 10.998 plus or minus 0.0039. Okay, that is the interval, the parts of the interval, and when we do the whole thing and express it fully as the interval, it will look something like this, that the upper limit, when we add 0.0039 to this, the upper limit will end up being 11.002 inches, and the lower limit will end up being 10.994 inches. Now, if you look at that interval, remember we want the mean length of the paper to be 11 inches. We have a 95% confidence interval that the true mean value is in this range. But if you notice this range actually contains 11. Since it contains 11, we have reason to believe that the true mean has not changed. Okay? We have good reason to believe that the true mean has not changed. So keep that in mind here. This just sort of show you a picture of that. So here's 10.994, here's 11.002. Well, if that's the case, 11 is somewhere around. Okay, 11 is somewhere in here. So since 11 is in the interval, we have no reason to believe that the true mean is not 11 inches. So there's no need to actually go ahead and change that. All right? So I want you to know how to write the statement, though, around the confidence interval. So you should be able to write this and say, we are 95% confident the true mean, whenever we say true mean, we mean population mean. The true mean length of the paper is between 10.994 inches and 11.002 inches. Can we be wrong? Yes, we can be wrong. And we have, because this confidence interval is a 95% confidence interval, it means that there's a 5% chance that the interval does not contain the mean. So you make a note, there is a 5% chance the interval does not contain the mean, mu. Okay. So we gamble that it's actually in there, but there's a risk that is not in there, and that risk is a 5% chance. Okay. So we have to assume, as we said, that the sampling distribution is normal. Actually, we were told that since we know the sample standard deviation, we do not need to assume that the population is normal, right? But the sampling distribution is indeed normally distributed. 1 sigma is actually known. Okay. Now, I want to draw your attention to something called the margin of error in our estimate. Let's see what I'm talking about. Now, the confidence interval we found for this problem for mu was 10.998 plus or minus 0.0039 inches. So this piece right here, we call it a point estimate. Remember that. And then remember we had a critical value times the standard error. But this term right here, we will refer to it as a margin of error. A margin of error, which means that is the margin of error in our estimate. We take the point estimate and we allow for 0.0039 inches to above it and 0.0039 inches below it. So we refer to that as our margin of error. Okay. Now, in some cases, the margin of error that we have in our estimate is okay. We're happy with it. In some cases, we're not happy with the margin of error. It could be too large, and so as a result, we tend to want to reduce it somewhat. So if we want to reduce that margin of error, what can we do? Well, let's take a look at what the margin of error is. So margin of error, ME, and your book actually sometimes puts it as just E, the error, would be the plus or minus part of the confidence interval, which is Z sigma over root N. So look at what happens. It's a function of Z, sigma, and N. But we cannot control the standard deviation of the population. We could decide what level of significance we want, and we could decide what sample size we're going to take. So two things are within our control. If we reduce the value of Z, we could certainly reduce the margin of error, but look at our confidence level. What happens to it? When Z is smaller, the confidence level drops. Okay, it shouldn't be too hard to see. If you look at that, if this is 1.96, then we know this is 95%. But if we were to use one standard deviation, 1.0, right? Negative 1, positive 1.0. Remember, this is 68%. So that 0.68 means that our confidence level will be down to 68%. So we could shrink Z, but it reduces our confidence level. We don't want to do that. So the other thing that we can control for the same level of confidence is the sample size. And you notice as we increase the sample size, we could actually reduce the margin of error. So with this formula, we could specify that the sample size that we need for a given margin of error is Z times sigma over the error squared. And the way we get this is actually just by doing a little bit of algebra. We just change the subject of the formula. Because we have a square root of n on the right side, we would square both sides. Square this side and square that side. So if we square this side, the z becomes z squared, sigma becomes sigma squared. The square root of n, the square root would disappear, and then we switch the places between e and n to make n the subject of the formula. When we switch the places, we get this formula right here. Okay? So say if we wanted to find a sample size that would allow us to now estimate the paper length within 0.002 inches, what would our sample size be? So now we're going to do an estimation. So sample size estimation. Okay. In this case, we'll say E is equal to Z sigma over n. Over the square root of n. But we already have the formula, so I should just sort of stick with what we've already calculated. So I'm going to switch that back and say n is equal to this over E squared. So now let's substitute. We want the same level of confidence, so it's 1.96 times, we have the same standard deviation, we're assuming that is the same, which is 0.02. And then our margin of error is now 0.02. So that's what we're looking for, a margin of error plus or minus 0.002 inches. So we're going to substitute that for E, and we must square that. When we square that, value becomes somewhere approximately 385. That's our sample size, 385. So notice that we jumped now from 100 to 385. And that's our sample size that we need to get an estimate to within 0.002 inches. All right? With the same standard deviation and a 95% level of confidence. So we'll need at least 385 sheets. So I hope you appreciate that, the confidence interval and the calculation for sample size. Recap that. Confidence interval is the point estimate plus or minus a critical value times the standard error. For the case of the population mean, mu, if we're trying to estimate that, then our point estimate is the sample mean, plus or minus z when sigma is known, and the standard error is sigma over root n. Okay? Very good.